Hello everyone, I'm Shankha Subrasanian. Well, today's session I begin with a small but powerful quote. Always remember, failure lies not in falling down. Failure lies in not getting up. In life, you'll come across a lot of situations wherein you would not be, will be able to accomplish your goals in the first go. Maybe there will be hiccups in life, but remember that you should not lose hope. You should go on trying, and that's how you can achieve success. Well, we are in the midst of our discussion on sound, and this is a lecture which is dedicated to that. So let's, without wasting any time, begin with the session.
A body clamped at one point, when disturbed slightly from its position of equilibrium or rest, starts vibrating. The vibrations so produced are called the free or natural vibrations of the body. The period or frequency of vibration depends on the shape and size or even the structure of the body. The time period of a freely vibrating body is called its free or natural period. Each body capable of vibrating vibrates with a constant natural frequency. The amplitude of a freely vibrating body remains constant. The free vibrations of a body actually occur only in vacuum, because the presence of medium around the body offers some resistance, due to which the amplitude of vibration does not remain constant, but it continuously decreases. Thus, the periodic vibrations of a body of constant amplitude, in the absence of any external force on it, are called free vibrations. Let us check some examples of free or natural vibrations. If the bob of a simple pendulum is displaced slightly from its mean position, it starts vibrating with its natural frequency, which is determined by the length of the pendulum and the acceleration due to gravity at that place. Different pendulums having different lengths will vibrate with different frequency. That is, they will have different natural frequencies. A simple pendulum of length, say 1 meter on the Earth's surface, where acceleration due to gravity is 9.8 meter per second square, has its natural frequency as 0.5 Hz. A load suspended from a spring, when stretched or compressed and then released, starts vibrating with its natural frequency. Its period is determined by the hardness of the spring and the mass of the load. The time period will be different for the same load on different springs, and it will be different for different loads on the same spring. When a tuning fork is struck against a hard rubber pad, it vibrates with its natural frequency. The vibrations from longitudinal waves in air, which when reach our ears, sound is heard. This sound is of a single frequency and is known as a pure note. Similarly, when we strike the keys of a piano, various strings are set in vibrations at their natural frequencies. When an air column in a flute or an organ pipe is made to vibrate, it vibrates with its natural frequency, which is inversely proportional to the length of the air column. In a flute, the notes of different frequencies are produced by changing the effective length of air column when different holes in it are closed. In an organ pipe, open at both ends, different modes of vibrations are of frequencies in the ratio 1:2, 2:3, while in an organ pipe with an one end closed, the frequencies of different modes are in the ratio 1:3:5. The free vibrations are the simple harmonic vibrations under the restoring force, the amplitude and frequency of which remains constant. Once a body starts vibrating, it continues its vibration with the same amplitude and same frequency forever. The vibrations of a constant amplitude can occur only in vacuum. Since in practice it is impossible to have vacuum, it is very difficult to realize such vibrations in practice. In practice, the surrounding medium offers resistance or friction to the motion. So, the vibrating body continuously loses energy, due to which the amplitude of motion gradually decreases. It is our common experience that when a body is made to vibrate in a medium, the amplitude of the vibrating body continuously decreases with time, and ultimately the body stops vibrating. Such vibrations are called the damped vibration. Thus, we may say the periodic vibrations of a body of decreasing amplitude in presence of a resistive force are called the damped vibrations. The amplitude of motion decreases due to the frictional or resistive force which the surrounding medium exerts on the body vibrating in it. The frictional force at any instant is proportional to the velocity of the vibrating body, and it has the tendency to resist the motion. As a result, the vibrating body continuously loses energy in doing work against the force of friction, and so its amplitude gradually decreases. After some time, when it has lost all its energy, it stops vibrating. The energy lost by the vibrating body changes continuously to the heat energy, and it gets dissipated in the surrounding medium. Let us take some examples of damped vibrations. When a slim branch of tree is pulled and then released, it makes damped vibration. Similarly, a simple pendulum oscillating in air, or for that reason in any other medium, execute damped vibrations. A freely or naturally vibrating body in a medium cannot maintain its amplitude of vibration constant due to the presence of damping forces of the surrounding medium. However, if the amplitude of vibration is kept constant by applying an external periodic force such that the external periodic force compensates for the loss of energy in each vibration due to the damping forces, the vibrations of the body are called forced vibration. Thus, the vibration of a body which takes place under the influence of an external periodic force acting on it are called forced vibrations. When an external periodic force is applied on a vibrating body, the body no longer vibrates with its own natural frequency, but it gradually acquires the frequency of the applied periodic force. The external applied force is called the driving force. The amplitude of forced vibration depends on the frequency of the external force. If the frequency of the external force is different from the natural frequency of the body, the amplitude of oscillations is very small. But if the frequency of the external force is exactly equal to the natural frequency of the vibrating body, the amplitude of oscillation is very large. However, the amplitude of forced vibration does not change with time. Let us now take some examples of forced vibrations. When the stem of a vibrating tuning fork is pressed against the top of a table, the tuning fork forces the tabletop to vibrate with its own frequency. The vibrations produced in the tabletop are the forced vibrations. The tabletop has a much larger vibrating area than the tuning fork. So, the forced vibration of the tabletop sends forth a greater energy and produces a louder or more intense sound than that produced by the tuning fork. The vibrations produced in the diaphragm of a microphone sound box with frequencies corresponding to the speech of the speaker are forced vibration. So is when a guitar is played, the artist forces the string of the guitar to execute forced vibration. In the stringed instruments provided with a hollow sound box containing air, its strings are made to vibrate by plucking to produce forced vibrations in air of the sound box. The surface area of air in the sound box is large. So the forced vibrations of air send forth a greater energy and cause a loud sound. When a body vibrates under the influence of an external periodic force of frequency exactly equal to the natural frequency of vibration of the body, it is said to execute resonant vibrations. These vibrations are of large amplitude. Thus, resonance is a special case of forced vibrations. When the frequency of an externally applied periodic force on a body is equal to its natural frequency, the body readily begins to vibrate with an increased amplitude. This phenomena is known as resonance. The vibration of the large amplitude are called resonating vibrations. So what do we find? What is the condition for resonance? Well, resonance occurs only when the frequency of the applied force is exactly equal to the natural frequency of the vibrating body. Thus, at resonance, a loud sound is heard because the vibrating body vibrates with a very large amplitude and sends forth a large amount of energy in the medium. Now let us discuss some examples of resonance. The first in the list that comes to my mind is the resonant vibrations of pendulum. If two pendulums of same length are suspended from a rubber string and one pendulum is made to vibrate, the other pendulum also starts vibrating with a large amplitude and in same phase because of resonance. Let's talk about the resonance in a bridge now. When a troop crosses a suspension bridge, the soldiers are asked to break their steps. You know why? The reason is that when soldiers march in steps, each soldier exerts a periodic force in same phase and therefore the bridge executes the forced vibrations of frequency equal to the frequency of their steps. Now, if the natural frequency of bridge happens to be equal to the frequency of the steps, the bridge will vibrate with a large amplitude due to resonance, and the suspension bridge may even collapse. The last example in this list of resonance is the resonance in TV and radio receivers. The tuning of radio and TV receivers is based on resonance. The radio and TV receivers have electronic circuits which produce electrical vibrations, the frequency of which can be changed by changing the values of the electronic components of that circuit. When we want to tune a radio or a TV receiver, we merely adjust the values of the electronic components to produce vibrations of frequency equal to that of the radio waves, which we want to receive. When the two frequencies match, resonance occurs, and only the energy of signal of that particular frequency is received from the waves present in space, leaving the signals of other frequencies which do not match with the frequency of the receiver circuit. The signal received is then amplified in the receiver set.
So this brings us to the end of this lecture. Well, as I normally ask you people, please do write to me. By now I believe you people are all aware of my email ID. It's sanyan.shankha@gmail.com. My dear students, please do write to me if you have queries. It would be honestly a privilege on my part to be answering to your queries. Thank you so much for being such a good listener. Thank you.